Hello guys, thanks for joining this session. And today we have our speaker, Mr. Tristan Bergh, who will be taking a session on hypothesis testing. Now, to give a brief info about Tristan, he has studied aeronautical engineering, and then he moved into software engineering after a short career in helicopter flight testing. Tristan designed integration software in financial services before moving into distributed systems and big data. He now builds predictive analytics solution in the microinsurance industry using automated machine learning tools in PySpark. So guys, here's Tristan. He'll be taking over now. You all can ask questions via chat. Don't send your questions privately. Send it to everyone so that everyone can see what the question is, so that when Tristan addresses the query, everyone can know. So yeah, and in the last 10 minutes, we'll keep it for the Q&A, okay? So all the best, Tristan, and guys, make the best out of it. This session is for everyone, so enjoy.
Great, thanks Vijay, welcome everyone. Yes, Tristan Bergh here, coming to you out of Cape Town. And yeah, my bio does talk a little bit about statistics. I studied aeronautical engineering, where we just did very basic statistics as part of our undergrad course to do with manufacture. And we did a few things to do with statistics, but hypothesis testing was still sort of on the horizon. To cut a long story short, I'm now, after a few career changes, from aero engineer and flight test through to software engineer and now into data scientist, I'm finding it very, very valuable to start looking back at all the basics of statistics. So of course, one of them is hypothesis testing. So one of the really interesting parts of hypothesis testing is where it fits into data science. And of course, how do we do it? Means looking quite a lot at the theory that you're looking at. And then that brings us to the session overview, where I'll also then walk you through the steps to take a test on an hypothesis, and then tests that we can run. And there are many, many tests that we can run. And unfortunately, like most things in life, and in particular statistics, there are errors and uncertainties that we can fall prey to. I'm not sure how many of you are aware of Mark Twain, who said, lies, damned lies, and statistics. So he had a very low opinion of statistics, but done correctly, they can be extremely valuable. And so, yeah, point 5 talks to that. And then in 6, we'll dive a bit into the p-value and how we can get things wrong, and how p-values by themselves can be problematic. But again, there's always good news, and the good news is with appropriate application of the p-value testing and the hypothesis testing, we can certainly make some very valuable decisions, and possibly even influential decisions in our businesses. And then yes, as Vijay did say, there's a Q&A at the end, and we'll run through your chat questions that you submit. So let's dive right in. Okay. So to keep front of mind throughout this presentation, you'll know what hypothesis testing itself is, and that's a very key focus for us here. And we'll also know how to perform our own hypotheses test. You're going to get a bit of an intro into the terminology, and then there are some areas which can get quite thorny, and I'll try and point those out, in particular to do with which tests and how to sort of navigate yourself through the roadmap of which tests perform. You'll know which Python languages, language libraries you can use. You'll have that roadmap, which I've already mentioned. It is quite interesting that it talks to things like continuous, discrete, categorical, and interval type variables. All of them sort of help you decide which hypothesis test to run, among other things. And then you'll have a roadmap based on your data. Do you have intervals? Do you have categorical variables? And then we get things like numerical and ordinal, but we'll get into that. And then most important, how to avoid making any errors when you run your hypothesis tests, because this is a very, very abstract place to be thinking. And yeah, we're working in unknowns essentially. And one of the things that hypothesis testing does do for us is it helps us to know what we don't know. And it's key to know those aspects of the hypothesis test. So Now, having talked into all the sort of high-level theories, I chose to place forecasting probabilities and hypothesis tests in data science. So here we have a graph, a diagram really, with the running from transactional, which I would take to mean online transactional processing in a business, right the way through to strategic business inputs. Which market should we go into next, in which country, from is a potential example in a strategic sense. And then on the vertical axis, we have aspirational to advanced. And aspirational is just, I suppose, talking to folks who have lots of data and aren't doing anything with it, to descriptive analytics, which is where we report on what's happening, and we just show what the data are telling us, through to diagnostics, and as we can see, there are predictive issues in data. And with the red arrows, I'm highlighting where hypothesis testing fits in the whole process of data science. So it's not going to help you understand patterns across an entire data set, but what it will do with careful choice of variables is help you identify which are the variables that are important in looking at your outcome, which are the variables that are influential in looking at your outcome. Something else I'd like you to bear in mind while we're on this is a very interesting application for p-values, computing the p-values per variable, is in actually generating a machine learning model. And one of the techniques I have used quite successfully to create very robust models is to select variables for building a machine learning model out of a large set of variables, so that the model is not overfitting, and you can choose and tune your level of significance so that you use only the variables that have a very, very low p-value. And what this generated was, in logistic regression, was generated models that were very, very good at predicting. They generalized really well because they weren't predicting on noise or variables that were not significant in the feature set. And I can answer questions about that later. It's just, we're not going to dive into that now. It's beyond the scope of this presentation, but it's certainly something very, very interesting in terms of where you can also practically use p-values in building machine learning models. Okay, and as you can see there, as the graph goes to the right, it goes up like a good y equals x plot, from diagnostics through to predictive through to semantic. So afterwards, we can perhaps discuss ways in which you can increase predictive power of your models. But for now, the focus is very, very, very heavily on the diagnostic side. Which are the variables that we're looking at and what are they doing in our data sets? Right. Now let's look at what hypothesis testing is. This is where things get very fascinating, because as data scientists, as statisticians, with a small amount of sampling, we can do some pretty powerful things with the techniques and tools in hypothesis testing. So what is it? It's a guess. Something in the world around us is happening, and we're guessing that the thing that we're doing is influenced by or not influenced by certain other things that we can observe in the world around us. So one of the things we're doing is we're guessing, we're observing, we're applying our insights as human beings. So of course, as human beings, we are the wetware in a world full of hardware and software. And so we can talk about the chaos that possibly could generate. But this is hypothesis testing distilled. It's a guess. It must be testable. So it might be an interesting hypothesis to say, because of climate change, Tesla will generate facilities to produce millions of Tesla electric vehicles by the year 2025. Again, not really testable. It's also in the future. It's fun to speculate, but hypothesis testing isn't that. It's not speculation. It's taking physical observations or observables that we can test after we measure them. And what we do when we state the guess is quite important. So the hypothesis testing has these two elements, the primary elements. One is that we specify what our general understanding is of what to expect. And I'm going to harp on the throwing of flipping of a coin, because that is the code example we're going to be working through. So we generally understand what happens when a coin gets flipped. and that is that it can go one of two ways, or there is a 50% chance of one side versus the other landing on the ground. Of course, someone might have a biased coin, or they might flip it in a certain way, or they hide it when they pick it up, or the favorite one of scam artists is it's a coin with two heads, which I think is the maximum bias that you can have. And then the other one is our alternative guess about the result. So looking at what's happened. So let's say we're watching a person flipping coins, and it's heads, and it's heads, and it's heads, and it's heads, and it's heads. Then maybe we're saying, right, maybe there's something wrong with this coin. So my alternative guess is this coin is biased. And then we measure the outputs of an experiment or a sample of the thing we're guessing about. So this is really what completely excludes future speculation and about things we might measure. We need to be able to measure or take measurements from an experiment performed in the past. And then we test our measurements using statistical tests, and then we draw our conclusions based on the output of the tests in a very carefully set up series of parameters. So just to recap, hypothesis testing is these two elements. We must be aware of the general understanding of what to expect in a result, and then the other one is our alternative guess. So thanks, Vijay. So what we have now is the two sections of our guess, the general understanding and then our alternative. And let's look at how that looks. So in order to set up and run an hypothesis test, we could write it down. Generally a good idea, because I tend to forget things 5 minutes ago. So that would certainly help me. And then we get to the thing called the null hypothesis. Okay, which is also generally the generally accepted or generally understood null hypothesis or understanding. So, and then there's the opposite of what we want to call hypothesis, because what we're doing is we're saying accepted understanding, as I said here, the general understanding of what to expect in a result is generally our understanding. Beg your pardon, I'm just having to switch to a better internet. So can you still hear me, Vijay?
Yeah, I can hear you. It's clear.
Okay, great. Is it still clear and great? Okay, great. Okay. Yeah. So, am I clicking through has changed things, right? So. Back to that slide. So we have the null hypothesis, which means the generally accepted understanding of the thing we're observing. And then we have the test statistic. And that's a formula depending on our test type of the model, the hypothesis, and the data. And we use then the computed value to reject the null hypothesis with a given level of uncertainty. And that uncertainty is set up using significance boundaries. Or we fail to conclude and accept the hypothesis until future studies reject it. This is still quite complicated, but I think it'll get a bit clearer as we look at an example. So here's an example of a statement of hypothesis. Remember, I'm running the example of someone who's flipped a coin and it seems to be landing on heads a suspiciously large number of times. So my hypothesis would state, I think this coin is biased and will land on heads more often than a fair coin. And another statement would be medicine A will help people recover from influenza faster than medicine B. That's an interesting one because the null hypothesis is already inherent in one of two medicines, and then we can unpack that further in terms of the problem. And then the other one is giving a child a tablet computer reduces their reading skills. So notice the null hypothesis talks about measurement of things like the fair coin. We generally understand what a fair coin will do. That is the 50% chance of landing on either heads or tails. So we're observing that we would like to have seen more tails in the coin flips. Medicine A and medicine B are interesting because which of those is currently on the market and has a testable effect on influenza recovery? So that would be, the null hypothesis would be better or worse than medicine B. So medicine A is tested as part of our alternative hypothesis. And then in the third example, giving a child a tablet computer reduces their reading skills. We have to have a generally accepted level of what their reading skills are. So that's things like, would we measure it using a comprehension test or a subjective test by a teacher, or the ability for them to get words right in a particularly tough text passage. So how we measure things starts to come into setting up the null hypothesis. But it's really, really important that we set the baseline for what we're doing using the null hypothesis. So if I can just pop back up another slide. The general understanding is the null hypothesis, and the other part of the hypothesis, or the guess, is our alternative guess, and it's based on our observation or our experimental plan. We want to test medicine A and see if it will speed up recovery time or reduce number of days of symptoms, which is testable and measurable. Right. And we've been through that slide and we've talked about some examples. All right, and let's go on to the next slide. So I'm going to walk you through some terminology, and I'm going to talk a bit about data typology, which is ordinal, interval, numeric, or categorical, among others. There's still some debate in the statistics community about setting up data typology. And something else just to bear in mind is we're often sampling from a larger set of data, and those data will be distributed in a particular way. If you're really, really interested in this, there's some very good documentation on the central limit theorem. And what we're doing here is, as we proceed, we're assuming that the data sets that we have sampled are normally distributed or Gaussian distributed. But again, if you submit some questions on that, we can look at it in the Q&A. And as I said, our assumptions are important here. We're assuming a few things. One of those is that our data are fitting within a particular distribution. And just to complicate matters, which we won't dive into here, so don't worry about it, there is a way to deal with data that aren't part of an assumed distribution or the normal distribution. And we'll get to that in limitations as well when I talk about the errors that we have, and something else to think of, which is called statistical power and effect size of our samples. So that's a lot to unpack, and I am asking you to keep things in mind, but bear with me, we will get to some code where we'll be able to have a look at what's going on. Okay, next slide. So some fundamental terms we have. The population is the number of things we measure, and we want to build meaningful insights about that population. So often we don't even have the ability to see the full population, and we're sampling from the population. And so what we call the sample size is n, beg your pardon. It's a subset of the population. And in general, when we do statistics, we are always working with a subset, because it's pretty difficult testing the length of time someone is exhibiting flu symptoms in every single person who has flu simultaneously around the earth. It's quite tough. Now, of course, it might be doable with a very, very strong distribution of smartphones and a really cool application on those phones. But yeah, pipe dreams. And then the mean, it's the average of the value we're examining. I think we all kind of know what the mean is. It's called X bar. The values divided by the number of samples in the population. And the expected likelihood of our null hypothesis, that's our expected probability. So for example, in a coin flip, we're expecting a fair coin will land on one side 50% of the time, and on another side 50% of the time. And also we're assuming that if you test this and you flip the coin over time, you will get one or the other, and a 50% for either. Variance, and this is the quite a mouthful. It's the expectation of the squared deviation of a random variable from its mean. So this is a way of characterizing how our data fall when we sample. But of course, in a coin flip, it relates, it's a one or the other. And because of the fact that it's a coin flip, we take quite a particular distribution. It's called the Bernoulli distribution. don't worry about the fancy name for the distribution. It is a normal, it's a binomial distribution, which is a subset of the normal distribution. And it's set up so that we can model things like a coin flip. Then we have a term called the variance of the mean. So we also, not only do we look at the variance of the actual values, we look at the variance of the mean, and that's sigma squared over number of samples. And then we look at the standard deviation of the distribution, or how the values disperse from the mean. And this talks to, as I said before, the distribution. And this is best understood as a graph. Another way to describe it is we're looking at setting up a likelihood of where that value will be based on where it fits under the curve of the distribution. And I'll show you that in a little bit. Right, so just to recap, we've looked at some fundamental terms here, some basic ones, the population, the sample, and the mean. Some that are quite complex, like the expected likelihood of the null hypothesis. And in this case, it's relatively simple, 50%. In the case of medicine A or medicine B, it would be related to actual test results of medicine B in the industry that we would then use to see whether or not our medicine shortens that time. So that likelihood would be set up by us looking at the prior tests. We're using an interesting distribution that is specifically assigned for a binary case, a 50-50, a 1 or a 0, and it's a subset of a normal distribution. Right, let's look at what we have. Now, let's unpack some extra examples. An hypothesis is an educated guess, so it's a guess and it's educated. Another one would be over and above the medicine, a way of teaching that you think might be better. Another one would be a possible location of new species or a fairer way to administer standardized tests. I included this slide because I'm quite keen that you start to look at the world around you and start to make your own educated guesses about what you're seeing. Traffic, quite an interesting one is potholes. Would a new type of road surface change a pothole? How would an increased service interval reduce the chance that my car would break down? If I don't carry my bicycle pump, does that increase the likelihood of me getting punctures? I'm quite a keen cyclist. Okay, so please think about areas in your own world where you could administer an hypothesis test and convince yourself whether or not your results are significant, because that's the power that you're going to have after this test, after this presentation. Right. I'm now going to dive even further into stating the hypothesis. So as we've said before, it's a really good idea to write the statement. And the basic structure is, if I do this to an independent variable, then this will happen to the dependent variable. So what the independent variable is something that we have the ability to influence directly. And then the dependent variable is our measured outcome. And here's some extra examples for you so that you can really get a feel for how to state an hypothesis test or an hypothesis. And the statement here is, if I decrease the amount of water given to herbs, the herbs will increase in size. That's an interesting one. What are some other variations on herbs? If I pluck lemons from a lemon tree, then the lemon tree generates or produces more lemons in a given time period. What else would be interesting? If I prune a herb, it will increase in number of leaves, or it will grow faster, or it might grow slower. So I'm just suddenly at a loss in terms of ideas on herbs, but there we go. That's certainly something that you could test at home. If you have a plant on a windowsill, you could set up an experiment in day-to-day, run it over a certain number of days, and check the growth on your plant. But there is an interesting one. It's in sample size. And just on that, I can jump into a bit of a limitation. Generally, if your sample size is very small, and we accept most of the time that anything under around 20 samples is a problem, you are probably going to run into difficulties with your hypothesis testing. Look at the next one. If I give patients counseling in addition to medication, then their overall depression scale will decrease. So that's an interesting one because healthcare measurements are sometimes quite tough. That would probably require all sorts of input from the psychiatrists and counseling over time. Can you think of what would happen if you ran that test over a very short time, 2 weeks, or over a very long time, 2 years? How would that change things? And how would that relate to things like statistical power and effect size? And then if I give exams at noon instead of 7, then student test scores will improve. I'm not sure if any of you are aware of recent studies about teenagers where it has been found that teenagers really, really struggle if they don't sleep very well. So few schools have accepted some of the results of studies that had hypothesis tests done in them. And schools for teenagers are starting to run lessons from a later time in the morning. So I find that very interesting. And then if I look in a certain location, I'm more likely to find new species. If you're interested, there's a very interesting predictive model on that. It's the gradient boosted tree, and it was specifically set up to predict finding new species of a fish in and around the islands of New Zealand. So that's a real example in the world. And depending on your industry, I'm sure you can come up with all sorts of extra bits of information on hypotheses you could possibly test. Right. How do we compute test statistics? Okay, so we've talked about the hypothesis test. We've talked about writing down your guess and then writing it down in a reasonably good structure for hypothesis testing. So if I do certain thing to this independent variable, it will result in this certain outcome of the dependent variable. How do we get there? Well, we run a statistical test. I have talked a bit about various types of test. For example, on our coin flip, we're going to be using a hypothesis a test statistic called the Z-test. And what we're going to do, let me just check where the question is. I don't have the questions up on my okay. So am I correct in saying, Vijay, the hypothesis is we're going to apply something on a whole population which we concluded on a sample data? That's an excellent question. What we generally are looking for is, yes, we are looking to find, based on our hypothesis, something that we would apply on the whole population. And that's what we call inference. So that's part of what the hypothesis test does. It assumes a certain amount of, what should we call it, outcomes on the entire population based on what we're doing with the sample. So we are running hypothesis tests, yes, so that we can perform an action or take an action or measure or influence the population in a certain way by doing something with a certain variable. Yes, so that's exactly right. Great question. Cool. So where we are now is test statistics. Okay, so what I'll do from now on, folks, is I'll just move the chat window around on my screen. Okay, so what is the test statistic? Okay, so as I've talked about before, the fair coin flips. The medicine A will not help a cold sufferer recover faster than medicine B, or a child given a tablet computer will score the same on a reading comprehension test as a child without a tablet computer. So what is the null hypothesis for the coin flip experiment? Answer in your heads, and I've pretty much spouted a lot about it a lot. And then the next question is, okay, we're going to be doing the Z test. What does it look like in Python? Right, so now I'm going to take us through the code. Right. So, so what we've got is I'm using Jupyter Notebooks, and this is absolutely stock standard Python. So Jupyter Notebook out of Anaconda, and the interesting libraries for Python are essentially NumPy or I like to call it NumPy. Then you get SciPy or SciPy or SciPy. I quite like the fact that you can pronounce it any way you like. And you import those, as you can see. And we call a variable number of flips 100. We have observed 100 coin flips. Right. And remember I was saying that we're observing a few more heads than we expected. Here's another interesting bit of probabilities and statistics. What is the likelihood of having a sequence of heads or a sequence of tails? And that's in the Bayesian world, and there's all sorts of tests you can run on that. So the more energetic amongst you are welcome to go and read up for yourselves on sequences of flips and their likelihoods for them. Right. So number of heads observed is 61. Now, is that enough to be suspicious, or would we find that answer quite by chance? Or should it always only be 50? Let's have a look. So the heads observed is 61. And here we have Q, as I said, that's the probability of the null hypothesis. A fair coin would land on one side or the other 50% of the time. So if we did 100 flips, we would expect to see 50, possibly, but we've only done 100 flips. What if the next one is a tail? And so in 101, we get only 61 heads, etc., etc. But remember, this is a probabilities. We could have seen this by chance. What if the the coin flipper is just on a lucky streak? So we want to also find out. We want to make sure that we're not getting this by random chance. And that's something else that the statistical tests are doing. They're working with the number of probabilities, the number of events that happen underneath, and we can, underneath the curve, and then we can see what we're going to get. On getting the data, we can chat at the end about all sorts of data sets. There are a number of data sets that ship as standard with NumPy, SciPy, sklearn, etc. Out in the wild, when you're busy doing hypothesis testing in a real world situation, the data would be something you yourself might sample. But we can chat at the end about data sources. There are a lot on the internet. I'll show you. I've also got a couple of the links open that I'm referencing through this talk, and we can go through them as well. I'll show you what they look like. Right. The sample mean is X bar. So that's the average, as I said, and that's a float type variable, the number of heads observed divided by the number of flips. And now we're going to compute the test statistic, and in this case it's the z-test, and the z-test's equation is the average minus the Q, the likelihood of a fair coin, multiplied by the square root of number of flips divided by Q times 1 minus Q. And that's to do with the test statistics understanding of what's going on. And so when we run it, we get a test score of 2.2. Okay. There are some tests where you work with the test scores. We could possibly look at that later, but for this purpose, we're just going to look at the test score as input into the calculation for the p-value. Now, this is to do with the distribution. So your p-value calculation changes depending on which distribution you're looking at, and that goes hand in hand with your tests, because the tests sometimes work with their own distributions. And in this case, we're using the scipy.stats library function in the norm package called CDF, or the cumulative distribution function, and that's the equation required to calculate the p-values. Now we're multiplying by 2 in this case because the distribution is symmetrical, and you can have the lowest 5% of the data and the top 5% of the data, and we're looking just at both of them. So what we have here is that the p-value becomes 0.028. So what do we get? Well, the significance level is 0.05. And that's a generally accepted significance level. It is slightly open to interpretation. When I was building very robust models for logistic regression, I used p equal the significance level of 0.005 and even 0.001, 2 noughts. So those were very, very, very small. So I was really, really making sure that the influence of the variables in my system were very, very definitely not randomly by chance influencing the outcome. But in this case, we can reject the null hypothesis and conclude that the coin is probably not fair. Okay, so I have a question on what is the hypothesis and the null hypothesis, and what is the p-value. All right, so let me go back to my slides, and we'll look at a few different ways to explain a p-value. So I'm going to bring you down to this graph. Right, so as you all can see, there's a symmetrical graph here. And what we have is, it looks like about what we call the bell curve, or a very smooth hat. And that goes by a large number of names, and it's the Gaussian distribution, the binomial, or the normal distribution, right? So what the p-value says is, what is the likelihood of us seeing an outcome sitting in either of these regions that is less than 5% or greater than 5%. So the p-value talks about the likelihood of us seeing something by chance. So what we're doing is we're saying 0.05 or 5% of the time, we believe 95% of the time we could see something by chance, but 5% of the time we won't. So we're really, really restricting our test of the data. So we're saying if the p-value is less than 0.05, then we're definitely not seeing this by random chance. And what that means is random chance is also the occurrence of the null hypothesis, because that's the general thing that happens. So we're saying if the p-value is tiny, we are definitely seeing an outcome that wasn't random chance, or an outcome that wasn't the null hypothesis. Okay, so defining p-value like that, I'm now going to go back to the hypothesis examples. Okay, so right, this is a reasonably complicated definition of the null hypothesis and the hypothesis. So the null hypothesis is the opposite of what we want to prove or what we are investigating, or the null hypothesis is the generally understood thing that will happen. There will be a rush hour between 6 and 8 a.m. every day. What is the likely, is it possible that if we put traffic bumps in the suburbs, we will reduce we will cause the peak hour to only be from 6:30 to 7:30. So the null hypothesis is there's always going to be a traffic jam in this area between 6 and 8 a.m. The alternative is, if we do this, we believe we'll get less traffic, or a shorter traffic jam time. So the null hypothesis is traffic jams. I also like that analogy because traffic jams are just a fact of life. Maybe I should talk about tax. So the null hypothesis would be a citizen in a country is generally going to be subject to income tax. So an alternative hypothesis would be if someone goes to Mars, but you see where I'm going. I'm doing a bit of an extreme there. So the null hypothesis is pretty much something that you're guaranteed will happen, and something we know a lot about, and something for which we have a known likelihood. That's also quite important, as you saw in the test. You can play with the numbers. I'm not sure if any of you know that the gambling casinos around the world are allowed to shift queue. So they're allowed to say, we're going to make our coins slightly biased so that we can have a few outcomes on our side so we can make money. It's one of the reasons why I'm quite loath to gamble, because in order to make money, the truly random casino games would not, they must be biased. Okay, right. How's everyone doing? I'm hoping you're all okay. did I answer the question? I see the question about p-value was from Pramod. So, oh no, yes, Pramod. So I see there's another one. So Pramod writes, we can conclude the null hypothesis we're assuming this happened by chance. If we calculate p-value, which is less than 0.05, we can reject our assumption and say it's happening because of some reason. Yes, what we're doing is we're saying the null hypothesis is going to happen anyway. How are we sure that when we run our test, we're not just having null hypothesis outcomes mixed in with our own test? And what we're doing is we're splitting them apart. And so we're saying when we reject the null hypothesis, we accept our alternative hypothesis. And so exactly right. We reject our assumption of the null hypothesis, and then we're allowed to say it's probably happening because of the reason that we have stated in our alternative hypothesis or our own opposite hypothesis. So let me just give you a view of a nicer, more simple way of stating the null hypothesis. So if I do something, then this will happen. So that assumes that the null hypothesis is understood. So for example, if I decrease the amount of water given to herbs, that's the alternative hypothesis, or the opposite from the null hypothesis, which is the herbs will not increase in size. Do you see where the null hypothesis sits in that statement? So what we're doing is we're saying, right, what is the likelihood that the herbs will remain the same size? And we need to find that out. So this is typically why we would run a control group in our tests, because our control group we leave alone. We don't change the amount of water that we would have been giving to them. So what we would do is we'd say, okay, I've got 30 plants and I'm going to give these plants, I'm going to, or let's say I've got the control group, we want more than 20 in each group. I have 80 plants and I'm going to give, for these 80 plants, I'm going to give water for a few days at X amount. After a certain time, half of them I'm going to decrease the amount of water, but the other half I'm going to keep the amount of water the same. So what I'm doing is I'm letting the plants run as my null hypothesis, and I will measure their size, because the alternative hypothesis is we will change the herb size if we do something. So what we want to do is, but it's, remember, it's we will change the herb size over and above what would have happened anyway, or generally happened, or happened by chance or randomness. So what would happen by randomness if we just give them X amount of water? Then we decrease the amount of water on 40 of the plants, and over time, we then observe whether or not they decreased or increased. Just something to be cognizant of, increase or decrease would be what we call a double-tailed test, and a t-test is normally used for those. But here we're saying the herbs will increase in size, so that's a single-tailed test. We're just looking at one side of the bell curve. Right. So Pramod, I hope I answered your question, and let's look again at, while we're here, if I give patients counseling in addition to medication, then their overall depression scale will decrease. What I'm seeing there is the null hypothesis is that patients are getting medication, and the null hypothesis is how much their depression scale decreased just on medication. So we would look at that likelihood and outcome. And then we'd say, right, and then in another group, we give patients counseling, and okay, is Sumitra okay? Thank you. So if I give patients counseling in addition to medication, then their overall depression scale will decrease, but decrease over what was happening just on medication. So the null hypothesis is linked into that statement, the hypothesis statement. And then if I give exams at noon instead of 7, then student test scores will improve. The null hypothesis there would be, if I give exams at 7, I get test scores that are known. But if I change the exam time to noon and then I give tests, the new test scores will be higher. or improved. So the null hypothesis is in that 7, the first part there. So the third one is quite interesting. If I look in this certain location, then I am more likely to find new species. So what does this tell us about the null hypothesis? In that case, the null hypothesis is I will find new species at a certain rate looking in certain places. But if I look in a different location, I will be more likely to find them. So we then would measure how likely it is to find a species in a particular location, let's say location A, but our test will be in location B. And then we count the number of species we find in B, and we run our test. Right, I hope that's clear. Let's have a look at the slides. Right, so let me go back to notebook 1, just to recap. So in notebook 1, we run the Z-test and we get a p-value of 0.028. So 61 is outside random chance for it being unbiased. Now, let me show you how the system works if I change the heads observed to 50. Let's have a look. So if I run that, look at the p-value. The p-value is now 1, which is kind of what we expect. Absolutely no way that this coin is unbiased. That is a fair coin. So our hypothesis, the coin is biased, doesn't hold. We can't reject the null hypothesis. Now look what happens. I'm going to change the numbers again. Let's change heads observed to more than 61. Let's do 70. Okay, that's proper. Let's have a look. Look at that. The p-value goes below the level that I can see in my formatting of 3 decimal places. But let's change it again. Let's go to 65. How's that? 0.03. Okay, so that's quite low. That's below 0.05. And if we go to 61 back again, we get our good old 0.028. So as you can see, when we observe more and more and more of the thing that's not what we're expecting, it's a problem. Yeah, thanks, Dario. Much appreciated, folks. I really appreciate this. I've dived into this in my own head, and one never knows really how easily one can communicate it out. So there we get a 0.028. So how do we get them from the distribution? Again, folks, I hope you don't mind. I'm just going to reinforce what I said earlier. We look at I'm going to skip past a slide, but we'll get back there. So here's the graphical representation of p-value. And as you can see, it shows us where our significance boundaries are sitting. Those are 5% significance boundaries, or 0.05. So we got it, the value we got wasn't here, it was less than 0.5%, and less than 5% of the values in the distribution sit under this part of the curve, and that's our p-value. So we can reject the null hypothesis. Right, let me get back to the previous slide because I really go into great detail about what's happening. So if we flipped a coin lots of times, the number of heads and number of tails would add up to a count pattern or distribution. And in this case, we use the Bernoulli distribution, which is a kind of binomial, or the bell curve, as I said before, also called the Gaussian curve. These are distributions that we choose. You choose a distribution as part of your statistical test. You can also have a look at it from experimental values. And then, as I mentioned right at the beginning, this is where the central limit theorem comes in, which is a complicated way of saying things converge on a particular distribution in the real world. And that is the Gaussian or bell curve or binomial distribution. So things converge on that distribution. So we're safe using it as a distribution to find out how many of our events would be happening to chance or can be attributed to chance, or how many of those events are sitting above our significance or less than 0.05. Right. We calculated the odds of 61 out of 100. Oh, beg your pardon. Sorry about that. So we calculated the odds of 61 out of 100 coin flips occurring by chance. So what we get is How non-random is 61? Or, as we've stated in our hypothesis, how biased is the coin? And 61, we have found, is biased based on the distribution and our test. But here's the thing. A generally accepted likelihood of significance is, as I said, 5%. So it means the null hypothesis is false, and we can conclude the coin is biased. And as I said earlier, we can reject the null hypothesis. The coin is unbiased. We're rejecting that. Or, and here's something that could be problematic. We only did 100 coin tosses. What if those 11 just happened by chance and we still got it wrong? So B, the null hypothesis is true. It's just bad luck or pure chance we obtained these values. We still can't make a conclusion. Maybe someone is messing with us with a magnet gun, a very strong magnet, and they're just pushing it so that the scam artist flipping coins on the street corner won't get caught by someone as savvy and p-value-y as ourselves. But keep that in mind. 3B, it's not cut and dried. We accept A, but it doesn't guarantee significance. It is likely, but not guaranteed. And I can't stress this enough. And so at the end of the presentation, there is a really, really good article called Statistics Done Wrong. It's here, and I would heartily recommend that you go and have a look at it. Is it that one? No, it is this one. statisticsdonewrong.com. It's superb. I heartily recommend you make sure you're familiar with the concepts done there. They talk a great deal about things like p-value hunting and all sorts of messing about that researchers sometimes do. Right, so we've gone through the logical flow of our code. We've gone through the graphical representation of where the p-value is making its discrimination. And now I've talked at length about the probability distribution, the binomial probability distribution. Just something to note here, the mu is the same as Q. They rhyme, lol. So mu is the average, or, and Q would be the 50% line. So that's the mean. It also is related to X bar. Mu is also X bar. Actually, negate that Q. I think it's mu is the average, X bar, beg your pardon. And as we can see in the distribution, this is where the p-value comes from. The percentage of values that fall in a particular place in the distribution are shown in the various colors. So 34% of the values and are above or below the mean number, the average. 13.6%, oh, and they're up to 1 sigma or standard deviation. This is also related to variance. Remember, variance is how far a value is from the average. And then we have the green, which is 2 standard deviations, and there we have 2.1% and 0.1%. So as you can see, a very small number of values occur under 2.1, and in this case, 2.1 plus 2.1 adds up to 4.2%. So in this case, that line dictates a 0.042 significance level. Right. Yeah, Bayesian analysis is super interesting. We're not going to get into it here. We'll just treat it as a certain test. If I can just jump ahead, Bayesian tests, I think, are here. Let's have a look. No, I don't see Bayesian tests. If someone sees a Bayesian test on this screen, just state it in the chats. But I don't see a Bayesian test here because these test statistics are not are frequentist, not Bayesian. Right. So let's go back to the terminology. Have we got everything here? Yes. So the entire population is assumed to fall under the curve. The sample is also assumed to fall to make this curve, even though the numbers are less. And it is assumed that the average for the sample is the same as the average for the full population. If it's not, there are issues. And I must say that's starting to get to the limit of my my statistical abilities. I'm not sure what relationships exist between averages in samples and averages in probability in full populations, but that's, I think, no one knows, and that's why we have statistics. Right. As I've shown you before, it's quite a confusing roadmap, but Here is the start on the left. Oh, beg your pardon. The start is on the top left of the screen, and we have nominal, ordinal, or interval ratio data. And those are to do with things like continuous, discrete, numbers, text, or categories. And an interval is, for example, age bins. So as you march through the map, you can see where we get to various tests. The scope of each test is outside the scope of this lecture, but I will just point out where the coin toss is. So at the start, we have an interval, 0 or 1, and we're looking at differences between groups of samples. We have one sample. So we go to the green diamond. Is there one sample? Yes. Is there a known standard deviation? Yes, there is, because we know the standard deviation of our distribution. And so we end up with the Z test. Right. Now, there are other tests that can be done. And these are outlined in there. And I've referenced it for you, so you can go and have a look at some of the discussions. The thing is, you need to start deciding and learning about how your data look. So what is an ordinal data set? And I encourage you to go and do your own reading on that. Right, now we're going to get into the p-value and errors. Now what we have here is, there is always the possibility that we found a difference. Our p-value in our coin flip was 0.028, but the difference doesn't actually exist. The coin flips were sitting at maybe 51, 52, and there was a proper fluke, and the coin flip had a series of 6 or 7 heads that isn't going to happen again because it isn't a biased coin, and we stopped measuring at that point. We would then have made what's called a type 1 error. But what would have happened if there is a difference? The coin is actually biased, and we didn't pick it up. What if the coin was really, really biased, and that person had a magnet, and they just flipped it to being only tails to bring the average down, and then we did our sample, and we got 52 heads and 48 tails. Again, less likely, but in this case. But a type 2 error is if there is a difference and we didn't pick it up. So our p-value is too high because we put in the wrong number, or we chose the wrong test. So how do we know if we've made these errors? That's a problem, isn't it? But how do we know? This is statistical power. And the statistical power concept is to do with whether or not the way you've sampled, the values you've sampled, the measurement you've taken, and your whole experimental design is powerful enough to identify any significant differences between your null hypothesis and your alternative hypothesis. So let me state that again. Statistical power is something inherent in the way you've set up your experiment, and it's also how you've measured. For example, what would happen if we were measuring the growth of the plants, and our ruler was in inches and we thought it was in millimeters? Or there's an error in an electronic sensor, or our calculator batteries are starting to fade and we're getting the wrong information out as we punch it in. Or we've got an old version of Excel and we think we don't, and we're running the wrong formulas. Things like that could possibly influence statistical power. But generally, it's to do with sample size. If you don't have enough samples, what if the street corner artist is taken to a big warehouse and stands in the middle of a giant warehouse, and then we do 300 coin tosses with that coin, and the coin was inherently biased? We'd get the 50%. So, or wasn't inherently biased, we'd get the 50% because there would be no magnet. But again, why would we want to do that, and how would we do it? And this is crucial. Statistical power, some folks even state that unless you state statistical power and effect size, which I'm going to get to in a moment, p-value and significance tests cannot be presented with confidence. So some folks say that as a given, and here it is. So in a book, The Essential Guide to Effect Sizes, Statistical Power, Meta-Analysis, and the Interpretation of Research Results, it was a book published in 2010, statistical power is the probability that a test will correctly reject a false null. And the statistical power has relevance only when the null is false. So again, another proviso, but it's certainly something to think of. So as I've mentioned, as the sample size gets bigger, the power of the test to discriminate increases. Related to that earlier question, if we have a very small sample size, you're on shaky ground making inferences about very large populations. As sample size increases, we are gathering more and more information and samples out of the population until, of course, if you sample every single person in the population, you have a perfect understanding. And then you wouldn't need an hypothesis test because you would know. So you could measure. So what you could do there is you would run your experiment and then you measure it on the entire population. But as I stated with the plants, I mean, imagine having 80 plants in your house and you're running that experiment. Quite tough. So these things generally tend to be, need lots of resources and can be quite expensive, especially when you start getting to drugs testing and control groups and all sorts of things. Right, so how much power is enough? We can calculate it using an effect size. So statistically significant results mean only there is a difference between our hypothesis and the null hypothesis. It doesn't mean that we found anything important. We have a number. So we can't, we can only state that there is a difference between the null and alternative hypotheses, not that there actually is a difference. This is related to the causation is not, correlation is not causation information. Let me just take you back to some of the statistical tests that you can run, and you'll see that some of them are correlations. So if you look right at the top in the orange diamond, correlations or variable relationships or differences between the groups, there are correlations, then we'd run Spearman's rank correlation. So you get a correlation is an hypothesis test. So causation and correlation are problematic. Sumitra, I'm sorry to hear that. I'm sure GreyAtom is looking after you. Perhaps if you can, if one of the GreyAtom engineers can have a look. Sorry to hear that, or sorry to read that. So back to where I was. So yes, correlation is an hypothesis test. And Spearman's rank correlation is to do with ordinal data sets, which are categorical, and you rank them so that you can start looking at different inferences between what's going on and what's happening in your sample. Right, so let's get back to statistical power, and I show you now what we're going to look at effect size. So how do you calculate effect size? So the equation is theta effect size is the difference between two means. One is the treatment group and one is the control group, or in our case, the treatment group is the measurements that we're taking that relate to our alternative hypothesis, and the mean of the control group or null hypothesis, the one which we're not influencing. And then the standard deviation of the control group is sigma, the control group, because remember, we're comparing what we're doing to the control group. So for example, in the medicine example, medicine A, medicine B, where we say our medicine can improve people's flu symptoms faster than medicine B, we would measure the standard deviation of length of time to heal from flu of the control group. Then what we do is we'd measure the mean of the treatment group, and we know the mean of the control group, and we run the equation and we get effect size. And it's a number between, that can be smaller than 0.1 and can get quite low, goes up to 2, I think. But if it's over 0.5, then there is a very large difference effect. So what's happening is your medicine A, if you get a effect size of greater than 0.5, your medicine A will have a big effect. Right, let's see what is next. Okay, so now we have effect size. How do we get statistical power from effect size? So you need to choose your statistical test to use. The independent t-test, which would be for the two-tailed stuff, you get a paired t-test. ANOVA, as you may have seen earlier, is to do with multiple variables at play. But in our case, if it's just number of days of influenza, we would probably not use ANOVA. The alpha is the level of significance. So remember that vertical line in the distribution. Where we put the vertical line is the significance level. And then if your p-value is less than that significant level, you have a significant p-value. Remember that. The expected effect size. This is interesting. You're not 100% sure, okay? So now we're getting into a very interesting part of iterating. So the expected effect size can only be calculated after collecting data. So you start initially with a chosen value. That is an aspirational value. I want this effect size. And of course, we want the best effect possible, but generally 0.5 is chosen. Then what we do is we calculate statistical power, and that gives us a value between 0 and 1. Less than 0.8, the sample size must be increased. Right, so let's look at the next code cell. So here, what I've done is using the same libraries, we get statsmodels.stats.power. Okay, so what I'm doing here is I'm going to be calculating a t-test indicative power from the statsmodels.stats.power library. There are a number of them, and they generally, the power tests generally link up with the statistical test. The effect size, what have we got? 0.5. Yeah, we want to make sure we have a good effect size. The alpha is our significance level, and the power, the statistical power that we're looking for is 0.8. So what pops out is the sample size that we will need for us to be sure that we're getting a sufficient statistical power in our analysis. So those are typical values, and this is saying 63 and not 20. So that's a very interesting result for me, I must say, because generally people say, oh, we've got 24 sample points and we can make a significant result from that. So what that means is we're probably going to have to accept that we're not getting, we're not going to have a sufficiently powerful or effectual test. So what we're getting is we're probably going to sit, if we have 20, we might sit in the 0.3 to 0.5, which has a moderate effect, or we might sit here, 0.1 to 0.3 with a small effect. So let's see what a sample size of 20 will do. What would the variables look like for a sample size of 20? Well, 0.8 we don't really want to change. 0.05, let's leave that because it's a standard p-value, significant limit for our p-value. So let's go down to 0.4 and see what the sample size looks like. Wow. So look at that. In order to get just a moderate effect of 0.4 and the same power, we're looking at an increase in the sample size. So it's counterintuitive, but it's to do with the test. What if we do that? So instead of 63, we go up to 81 if we change alpha. So if we change it back to what it was, 63, we change alpha to 0.02, we need more samples. What do we expect to happen if we decrease the power? As expected, the number of samples goes down from 63 to 50. So this is how we were, remember, 63. So that effect is quite interesting. I must say it is counterintuitive to get more samples with a less effect. That's something I'm going to actually have to have a look at. But there you go. That's how you calculate the number of samples for a particular effect and a particular statistical power. In fact, you can go and do that now on freely available published papers where they publish their data. And you can actually go and have a look using some of these power tests, whether or not the folks actually had sufficient statistical power in what they were doing. And in fact, when you look here at statistics done wrong, you'll find that many existing tests don't have a sufficient statistical power to be able to make their draw their conclusions, and that's quite a problem. Right, back to the presentation and how are we doing for time. So we're coming up to 4:10, so we've got about another 10 minutes to go. So what I will do is, I think we can start to wrap up, unless anyone would like me to talk about anything in particular in the presentation, but there it is. So we want power to be greater than 0.8, and our effects generally 0.5. All right. Vijay, everyone, is there anything I can reiterate or go over from the presentation? Otherwise, we can start with some QA.
Yeah, guys, if you have any questions, you can definitely just type in your question, and Tristan would be happy to address those queries. And yeah, that's all.
Thanks, Vijay.
Thanks, Tristan. Yeah. So
oh, yes, flow chart. Yes. Right. Bear with me. I'm going to. I want to bring up a page on data typology. Bear with me, I'm running through my my notes because on one of these pages I do have ordinals, intervals, ordinal. There we go. Right, so in order to navigate through this, nominal, ordinal, or interval ratio data, you need to have an idea of what your data types are. So for example, ordinal is a property where values can be counted. So as they show you here, characters of the alphabet are ordinal because we can call A the first, B the second. That's an interesting one. Oh, beg your pardon, sorry. Here we go. I thought that was wrong. It's categorical. So things that are categorical, like A and B are actually categories. So that's interesting. Ordinal data, there we go. There's a survey where like somewhat neutral, dislike or dislike a lot. And those are categorical, we also call them. So if you have categorical data, you would then come into here, the orange diamond. So correlation or variable relationships or differences between the groups. Are there groups or correlations? Which do you want to look at? So we want to look at correlations. We would then choose that one. Thank you, Pramod. Right, and then if you have a nominal data type, so let's look at a nominal data type. There we go. Now, this is the article I was looking for. So here we have more: binary, categorical, ordinal, binomial, count, real value, additive, etc., etc. So I'd recommend reading through this. And as I said earlier, the how to assign these variable types is still a bit of up for discussion. So yeah. I also have some extra code to go through. Remember I said there's Cohen's, there's the significance level attributed to Cohen. I have some code where we can run through calculating significance that way. Right, I see a question from Pramod, the difference between correlation and group. That's how you want to analyze what you're doing. So if you want to find the correlations or between variable relationships, to do that for ordinal data, you need Spearman's rank correlation. For group differences, then you are looking at looking at the measure types. So independent measures are, for example, with our coin toss, each coin flip is assumed independent of the one before, and repeated and independent, as you can see, are handled differently there. So the differences between groups is not something you can get a correlation on, because groups have multiple variables to do with them, whereas variable relationships and correlations inside those variable relationships are single variables. I hope that explains it. Right. So while we're here, I do have some extra code further down. So for example, here's code to calculate the Pearson's correlation between two variables. This I got from Machine Learning Mastery, that is this website. It's very, very excellent. And in fact, I have purchased one or two of Jason Brownlee's books, and he has an immense number of tutorials. He also shows you how to generate your own data, which can be problematic, but he shows you how to generate your own data in some of the tuts, and off you go. Right. I have 2 questions from Rajesh. Thank you. Could you help me in understanding PDF and CDF? So CDF is the cumulative distribution function, and a PDF is the probability distribution function. They're different, as far as I know, there are different ways to calculate things. So the cumulative distribution function looks like a step. There we go. So the cumulative distribution is a further transformation of the data. So, and then your distribution will have different ways of, your distribution will accumulate over a sum. That's what the cumulative means. So it's a different transformation of your data in the normal distribution. So the PDF is the probability distribution function that we've chosen. So for example, for the coin flip, we chose Bernoulli because Bernoulli is an allowed subset of the binomial probability distribution function, which itself is a variant of the Gaussian or normal distribution. So we're allowed to use that distribution in doing our p-testing, our significance testing using p-values. The cumulative distribution function is a calculation done to add things up. So that's a different transformation done after we have the probability distribution function. Right, when all is the null hypothesis required? You always have to have a null hypothesis, because your hypothesis testing needs to have, I suppose you could think of the null hypothesis as a baseline. It's the generally accepted fact, the baseline. It's something that it's something that we can observe that happens every day. It's already known. What else? The control group. So the null hypothesis is related to what the control group is telling us. So we have to have the null hypothesis in every case that we're doing significance testing with p-values falling inside or outside a significance threshold or significance boundary. So if you can't state the null hypothesis, there are other statistical tests you can do where you get variables from one group and variables from another group, and then you get parametric tests that are able to distinguish between groups without an assumed distribution function. Those are quite exciting to me, because there are a few practitioners. There is a chap called Nicholas Nassim Taleb who talks about the fact that we assume the normal distribution underlying everything, or in other words, we apply the central limit theorem to everything, or we apply it way too much. And he says, try and stick to techniques where you don't use the central limit theorem and you actually find out the distribution. But then again, we're back to our original problem, which is we don't know what the full population looks like, so we don't know how the data are distributed in the full population. I could try and find a website that shows what happens as you repeatedly sample. Your values start to do what's called converging around the mean. That's in other words, that's the central limit theorem. So what happens there is when we are sampling a population, we generally are safe, assuming that we are converging on the mean with our samples and that we're creating a normally distributed sample set. And then the null hypothesis will work because we can use the null hypothesis related to what's going on in our sample. When you don't have a very clear idea of what's going on, in fact, if you don't have a null hypothesis, you need to have a control group. And that is why there is a control group. It's when we don't know how to state the null hypothesis numerically. So we don't know the probability of Q. We don't know, in a coin toss, it's 50%. We know that up front. But in the plants, what is their growth rate normally or randomly or just by chance if we water their plants, what's their growth rate? So in fact, that brings me to a very interesting point. Would it be better with our control group of plants to water them with only a specific amount of water, or just randomly throw water on the plants? Which would be better? I'm guessing that randomly putting a water of whatever kind onto that group of 40 control plants is better than putting a very strictly measured amount of water on the plant. What we're doing there is if we put a measured amount of water in a control group, we're separating them away from being a control group. We're restricting the water we put on the control group plants. So what we're doing there is we are muddying, pun intended, the measured group of plants. So what I would suggest there is maybe even put the plants outside, and now we get into all sorts of areas with setting it up. Right. Is it always necessary to have normal or binomial Bernoulli, Poisson or others? Yes. You can have Poisson and other distributions. I haven't gone through all the possible statistical tests. That's quite a large undertaking. And as far as hypothesis testing is concerned, you do need to put quite a bit of work into the distribution that the test works with. Let's go to Jason Brownlee's page, and I'll talk to you about, beg your pardon. Go to Jason Brownlee's page, and I'll talk to you about the distributions of for the tests. So he has all sorts of tests here. I'm assuming you can all see it. Variable relationship tests, compare sample means, non-parametric, and so on. Now, when we go to a whole bunch of tests, let's have a look at what happens here. And let's observe the different distributions that get used. So what we've got is Shapiro, Wilks test. So what is happening there? What distribution does it use? It requires a normally distributed population, and the test statistic equation is well known. I'm going to move quite fast. Please type if I'm going too quickly. I'll try and keep it slow so that I'm not jumping around too much. Let's look at well, here we go. The sample has here's a test that compares between two populations where one has a Gaussian and one does not have a Gaussian. So they would still need to know what the underlying data distribution is. So that's understood there. You can test whether the data set has a Gaussian distribution using the Anderson-Darling test. I didn't go into this because this is just also quite confusing. Correlation tests require that the observations are independent and identically distributed. So as long as we know that the samples are independent, and that's another issue. There's a whole statistical lecture on sample bias. but we do have here that the observations are normally distributed. Okay, great. Spearman's rank. So it just wants them to be identically distributed. It doesn't specify what the distribution is, and so on and so on and so on. Identically distributed, beg your pardon. The chi-squared test, the contingency table are independent. This one I can't tell you whether or not it'll require certain distributions. Let's go have a look. So what I'm trying to show you here is, as I'm going around and I'm walking through the different tests that I've decided I need, I recommend that you do a bit of research around the test and that you take some time to be sure that you're in the right place with the test and its distribution. So the chi-squared distribution, so the chi-squared test, it's a statistical hypothesis test where the sampling distribution of the test statistic is a chi-squared distribution when the null hypothesis is true. So what it's doing is it's setting up a number of levers that, when they are pushed in a particular way, give you an output. So the distribution here is about the distribution of the test statistic. And so if the null hypothesis is true, the test statistic generates a distribution, and then you can test whether or not that distribution was generated. So the test statistic itself talks to all sorts of processing and logic. And so I know I've opened quite a can of worms for you here, but what I'm hoping is, with an appropriately specified hypothesis and an understanding of the null hypothesis and your alternative hypothesis, you are now well placed to go out and choose the right test and to choose how you're going to test for significance. Right, I'm going to move on to the central limit theorem, and the central limit theorem is talked about in Wikipedia as well. So what we have on the central limit theorem, well, you can see I've been there already. The central limit theorem says, in some situations, their properly normalized sum tends towards a normal distribution, even if the original variables themselves are not normally distributed. So I did state it a bit simplistically before. By the very act of sampling, we are generating a normally distributed data set on which we will be running our significance tests. I hope that has cleared it up. That's my understanding. It's by the very act of sampling a real world situation, we are creating a normally distributed sample, even if the original variables themselves are not normally distributed. And so let me check. I recall seeing quite a nice graph. Here we go. So can you all see the very spiky, I'm going to try highlight it. Okay, can you see the spiky graph over here? That's the original data set, this one. This one here, it's the original. If we do one summation, we get the top right graph. You can see it's a kind of like a bell curve with a little bump here and a little bump off to the right. If we do another sample, another summation, we get the middle one, the bottom left one, and another one, we get the proper symmetrical bell curve. So the central limit theorem states that if we're working with a real world sample and we sample and sum the instances that we get, and they will converge on the mean, is another word for it. They will become normally distributed. This is the law of large numbers, and it says that sample averages converge in probability, and almost certainly as we get to infinity, which again, it doesn't really help us much because we don't want to spend billions of dollars on setting up a test with 100 million samples. So here's another way of seeing the description in an even more simplistic fashion. So as you can see, mu, the population distribution is around mu and average, but look at the distribution. Let's see if I can highlight it. We're on this graph now. The population distribution has 2 peaks, but if we sample it, the sample distribution is Gaussian or normally distributed. I hope I've explained the central limit theorem for you well. And
thanks, Tristan.
yeah, thanks, Vijay.
Yeah.
And then we get to, there's the references, and they're in the slides. The links, the hyperlinks are there. They worked as of this morning. So yeah.
So guys, I'll just ask my team to share, this the notebook and recording for this webinar as well as the previous ones that were held for your reference.
Okay.
And thanks, Tristan. Thanks for this wonderful session. And I'm sure all the learners, might have felt that it was pretty helpful for them. And we will be keeping such sessions again in the future. We will keep it regularly. And guys, please fill the feedback form that I've shared with you. I'm sharing with you. Again, it's very important. And thanks again. And we'll keep you posted on the upcoming events. Thank you, Tristan. Thanks a lot.
Thank you. It's my pleasure. All the best.
Log on to GreyAtom's learning platform to unlock more free content. Subscribe to our channel and hit the bell icon for regular updates.